I'm going to talk about a couple trials that we had that were funded by the R&E board. This urea and urea source trial is my new study. It's an ongoing trial, and we actually have 1 year of data collected from it. So you're going to see some preliminary work and just kind of see what we're looking at doing. Focus mainly on looking at this fall spring urea question. And a lot of this is because some of the issues we've seen with corn production, some similar trials, seeing some poor performance of fall urea. And I know this is a practice that is used in sugar beet production. And before we made any change to any of our nitrogen best management practices, I wanted to make sure we had some testing going on just to see if we're seeing some of the same things with sugar beet production. Looking at some of the sources and the inhibitors are out there to see if they would increase performance of urea. So again, this will be mostly preliminary, just based on this fact this is the first year of data. What makes urea challenging is that it's not the same as anhydrous. It's a neutral molecule, which makes it water soluble. It's water soluble and it can leach itself without conversion to nitrate. We're always concerned about nitrate conversion and leaching, but urea mobility, it's good and it's bad because with surface applications, that's one of the things we say. If we have a 1/4 inch of rainfall, it's usually enough to effectively incorporate urea, where we don't have to worry about some of the issues with its loss pathways, namely volatility. And that's what makes it quite a bit different from anhydrous, is that conversion of urea from the neutral form over to ammonium is a process called hydrolysis, which doesn't stop when our soils hit 50 degrees. This isn't like nitrification, where we know that process slows down, and we can see some risk for loss, particularly for shallow incorporations, even in later into the fall until the soils freeze up solid. And that's one of my concerns, and one of the reasons really to look at some of the inhibitors right now, just to see if we can pin down what might be the highest risk of a loss pathway moving forward. So what we had in 2021, in 2020, we actually had 2 studies that we started that were just spring rate trials that we looked at biostimulants. The thing on those trials with the biostimulants, we didn't see anything with that. I'm not going to show that data, but it's a way to get more rate trial data. And that's one thing that I've been trying to do as I've been easing into more sugar beet research, is to try to compile some of the information, and getting some of this nitrogen rate data was been kind of top on my list. And this has been a bit way to do it and look at some of these other factors. 2 trials. I'm not going to talk much about the Crookston location. I'll have that information on the slide so you can kind of see the data, but it's not anything I'm going to discuss readily with this particular study. There's 2 trials at each location. At the Hector site, we had just a simple fall versus spring urea nitrogen rate trial. So 8 rates, 0 to 210 pounds, both fall and applied, where the rates for fall and the spring application were applied in plots right next to each other. And that works well to kind of test that timing component with most of these studies. The second trial, I picked a suboptimal rate of N. We did the same setup for the trial, but in this trial, we're looking at sources. So essentially what we're looking at is commercial inhibitors, ESN, different blends. I had AMS as well in that mix. I'll talk here in a slide and show you exactly what we used for that source trial. And everything was they're replicated 4 times at each location. So the sources we were looking at, 0 N control, and then we're looking at 100% urea as kind of the standard practice, and then looking at different blends of ESN ranging from 33, 66, and 100% of ESN as a total N in the mix. Then we had some of the commercial inhibitors, Anvol, which is one of the new urease inhibitors. We had that at the labeled rate at 1.5 quarts per ton. We're using agritane. We're using a low rate of it though, and what I was trying to do was use the rate that would match the amount of MBPT or agritane that's in Super U. Super U actually contains both DCD and agritane. The DCD would be a nitrification inhibitor. Obviously then the agritane would be a urease inhibitor. So it's trying to separate out if we saw a response to that product, was it agritane or was it the DCD? The rate we actually used in 2021, I had some coding issues, so I actually used about a half rate. We're targeting about a 1/4 rate in that because that's what's in the Super U. Instinct, it's been kind of the standard. I get a lot of questions on when people start looking at fall application of urea as a way to combat some of the loss pathways. Instinct Next Gen is the product. We had that at 24 ounces per acre. And the thing about this product that's interesting is that it's not a rate per ton in this product. it's a rate per acre. It's also a labeled pesticide, which has a supplemental label for sugar beet production. So it's a pesticide that can be used. The issue with this product and why we use the 45-pound rate is that's about the minimal rate I can use on it. Otherwise, it becomes soup when you look at mixing it. So it can be a little messy with that product. And then the other product I had, which wasn't urea, was ammonium sulfate. I wanted a 100% ammonium source, and that was the easiest one to use. So again, this study, I'm not going to get too much into this data on this side of it because I really need more years of data to really sort out between these things. But I'll kind of show you a few of the things that we were seeing with this particular study. It's kind of interesting because that's some of the things I've been focused on, looking at some of these loss pathways. So we have been looking at emergence data. That's been one of the questions. I looked at it when we looked at the spring application data, and we saw a lot of the same things as the spring application data from 2021, where you can see here these yellow triangles. This is looking at applied N as urea. So this doesn't factor in the amount of N in the 4-foot sample because we're looking just straight on application of nitrogen right before the crop and seeing the significant impact that it has on emergence. And this is emergence as percent of the planted population. I converted the two just to compare the two sites, and we're seeing roughly the same thing, about 85% emergence with no urea, and looking at about a 20 to 25% reduction with about 200 pounds of N applied, and it's a fairly linear response. The thing about the timing is what we did see is a significant reduction in the impact that timing had, particularly at Hector, where there really was no impact of the fall applied urea on emergence moving forward. And we saw that last year. And if you look at the yield data didn't follow the same trends. So even though we were getting a reduction in emergence, we weren't really seeing that impact yield beyond, where we're seeing yield relatively flat at the optimal N rate. So this reduction really isn't impacting things, even though it's measurable within most of these studies. We are looking at it in the source trial. Again, I'm not going to get too much into that. If you look at emergence, it did decrease with fertilizer application at Crookston, but actually at Hector, we saw a greater impact at the 45-pound rate with the nitrogen we applied, but the data is messy. And that's mainly because we have 10 treatments. So again, this gets into the fact that this is preliminary data. I'm hoping to get at least 2 or 3 more years of data out of this to look at an average across years, because it's really kind of hard to make a decision on this moving forward. But the only one that was significantly lower or the same as a control was Instinct. So that's kind of what we are looking at, with just looking at consistency of this is really it's going to be important moving forward. In terms of the rate trial, David showed some of this data. The fall versus spring really didn't matter. So we didn't see any difference between the two. We got the same exact yield, but again, it's a dry year, so I wouldn't expect to see as much of a difference between the fall and spring application. And that's why I want more years of data on this, just to get some wet years or some more normal years to look at performance, because where we've seen the fall urea really fall apart, it's been in the wetter years. But looking at applied N plus the 4-foot soil nitrate around 130 to 140 was the optimal at Hector for the given year. And again, looking at the 45 pounds, we're somewhere in here. One of the reasons where I'm using a suboptimal rate, because it's a lot easier to detect small differences between some of these sources if you're at a more responsive part of the curve. And really that particular part of the study isn't necessarily to measure exact efficiency, because what I'm looking at with that particular study is giving me some data to look in the future at maybe some rate trials, with picking maybe the top treatments that are separating out near the top for performance wise, if there is some differences between the products. Source trial. This was kind of the interesting thing. Differences at Hector, again, fall versus spring, weren't have impacted. The ones that were sorting near the top last year were the urease inhibitors or the 33% ESN, so these blue treatments. So this is kind of the thing that's intrigued me with this. And that's kind of, again, looking at this over time, seeing if these will shake out near the top, because this would point, if we see that the urease inhibitors be near the top, that, it may not be the nitrate leaching that is our biggest risk for loss with urea. It might be that urease activity that continues beyond that 50 degrees. If you have shallow incorporation, that it could be where we're seeing it. So that's really what I want to kind of get out of this by the end, to see, what that might be, where might be near the top with that, and see if that might be holding true, because that'll give me an idea in terms of what our major loss pathway is, because this hasn't really been looked at much. Even in the corn studies, we're factoring and looking more at nitrification inhibitors with that particular trial. An extractable sucrose, I mean, David showed this before, looking at not a lot of difference. If we look at that optimal rate near that 130 or 140, not a lot of difference between it, seeing that significantly drop off per ton. And you're kind of seeing the same trends if you look at tons per acre. So I'm not going to show that data for this, but again, looking at preliminary data with this, that if we're looking at it somewhere near the optimal level, there wasn't a whole lot of difference within some of those higher rates. So looking at a wrap up of this, again, preliminary data, we are looking at petiole nitrate contents. I'm trying to develop a database for this. The 2021 data we're still working on through 2020. We summarize that data, the cutoff here, around 850 part per million. Anything above that, we were at about max yield. Below that, we were anywhere from about 40% to 100% in terms of relative tonnage within that. So it may not give me a good way to look at a calibration to tell you how much to apply, but it's kind of whether you're good or bad, it gives me kind of a critical level of that. So we'll just kind of keep an eye on that, and that's what I've been trying to compile moving forward. The fall, spring were equally as effective. The only difference I saw was in recoverable sucrose. We saw about a 3% higher recoverable sucrose with the fall application, and it was consistent across the treatments. So that was really the only difference in timing we saw with the 2021 data. And again, dry year, will that stay the same if we have differences in terms of rainfall? Only time will tell with that. And then the source data, again, that's one of the things we'll be looking at, and it's very preliminary with that. So, I talk about seeing some better performance with some of these urease inhibitors. 33% ESN was also up near the top of the list. We'll just have to see, as time goes by, whether or not those are consistent, because again, that's just the primary, the first study coming out of this particular year. So I want to kind of change and look at switching topics here. One of the previous studies we had was looking at plant tissue. And, right now we're looking at the petiole, the nitrate contents, because that's been one of the questions. Is we haven't really been able to, looking at past data, to calibrate that test for looking at for management scenarios. But there were also some other questions just in general tissue concentrations themselves, because based on what I've seen the last 10 years or so after being here in Minnesota, we've seen more of an emphasis on collecting in-season samples with many of the crops. So what I've been trying to do with a lot of my work has been to look at how accurate this is, some of this data is to predict yield. The thing about it is it's nothing new, and that's one of the things we see this topic ebb and flow. It'll come in, it'll go, just in terms of interest, in terms of what companies are promoting this practices. And the sufficiency ranges, we know they're available. If you look at it, though, the sufficiency range is a thing. If you're taking samples, that these ranges are specific to a plant part taken at a specific growth stage. So that's one of the things. If you are collecting samples, there is a better time to take samples instead of just taking them randomly over the growing season. And that's been one of the things I've been stressing to a lot of people using this, is to watch what crop you have and what's the recommended stage, because there are set what they deem sufficiency ranges for a specific stage, but we see a lot of these concentrations changing over time, so it may not be consistent from one growth stage to the next. The majority of this data comes out of, if you're looking for it, out of the Plant Analysis Handbook 3. This is the source for a lot of this, which is just a compiled set of data for multiple crops on data looking at what they deem as sufficient tissue concentration values for a number of crops grown across the U.S. Sampling itself for beets, the recommended timing just for leaf samples is between 50 to 80 days after planting. So this puts a fairly wide range. You're looking at mid-June to mid-July. And that's one of the things we're looking at within this particular study, is sampling at 3 different times. So sampling mid-June, early July, and mid-July, because one of the things I want to see is consistency of the data. If we're sampling at the same leaf relative to the new leaf coming out of the top of the plant, what are our numbers? Are they consistent enough that we can use a single set of sufficiency ranges across that wide of a range that's roughly a month growth for the particular crop? Petiole nitrate, I think, has been studied more. again, I'll be looking at some of those numbers, and I showed you some of that data, and I'll kind of show you that, some of the nitrogen values were the ones that were coming more closely related to yield for this particular growth stage. But it wasn't 100%. So that's one of the things about this. If we're taking random samples from fields, it can really see a lot of variation in how some of these different nutrients are impacting themselves and impacting the concentrations within the plant itself. Can be hard to interpret some of this data. So the research was conducted from 2017 to 2019. These are all in the southern growing regions. There were 11 locations where 6 varieties were grown, and these 6 were the same across all years and all locations. So I wanted to be consistent, looking at some historical checks versus some new varieties at the time, and looking at varieties that had differences in yield potential and also quality. So trying to look at some different growth habits and some different ways that the tonnage and quality is produced, to see if there's any correlation with tissue nutrient concentrations. So our 3 targeted dates we were looking at, these are just the averages of what we hit, about 44 to 45 days after planting, 65 days, and then 87. So we're kind of looking at that a little bit more than that 80 days, a little bit less than the 50, but kind of as close as we could get it. And then trying to go about 2 weeks apart for sampling time at each of these individual locations. We sampled both the petiole and the leaf blade, and what we were sampling is roughly the 4th from the newest one that was coming out of the plant. So we're looking at the most fully developed leaf from the top. So the thing about these timings is we weren't sampling the same leaf in the canopy, but we're sampling the same leaf relative to the new growth within the canopy. And it became a little bit challenging at the 44 of these early growth stages because these plants are relatively small. And that's one of the things that I won't really suggest going that early, just because of the ease of sampling. It gets much simpler once we get more towards that 60 time frame for days after planting. So let's just looking at the data. I'm not going to get through all this. You just got to know that if we look at a variety and look at yield recoverable sugar, both in pounds per ton and pounds per acre, there were differences, and that's what we expected. And they kind of ranked out similar to what we had expected. And that's really what I wanted to see. So I wanted to have variability out there. And the short part of the story is that there was variability within these locations. So we looked at a number of correlations we were looking at about 14 different elements. So kind of running the full, what we call kind of the full, tissue report package. We'd have nitrogen plus ICP elements, which would be roughly 10 others, I think, on that range in terms of that. And looking at our strongest correlation was between petiole N and blade N with root yields. So seeing that sort out near the top, which would make sense if you look at the most limiting factor in these fields, likely was going to be nitrogen, even though we applied fertilizer based on recommended values. But it was going to be more likely that we'd see some correlation with that versus some of these other nutrients that were likely not going to be limited, just because of fertilizer applications are knowing from past research that we haven't seen a response to these particular elements within many of the fields across the region. Sugar content, again, leaf blade total N. So again, nitrogen being the strongest correlation. We had some negative correlations with calcium. But again, calcium content was not very predictive. So, a lot of what we see with these tissue concentrations, we see a lot of correlation with one versus the other, that it becomes a question then, what do we correct? If we correct one, will it correct the other? That's one of the things we typically see with a lot of the data, is that these major macronutrients can really impact growth, and which in turn impacts the concentration of some of these other elements. So that's one of the things about just going out and taking random samples within the field. You'll get a lot of things that might come back low. The question is, what do you fix? Do you fix them all, or do you fix one of them? Will they all become corrected just because maybe one of the major macros is affecting growth and uptake of other nutrients? So again, sugar production per acre, so recoverable sucrose per acre was similar to root yield. So again, really the short of the story here was that nitrogen really was the thing that was seemingly more correlated. And this is some of the data looking at blade total nitrogen concentration versus root yield, seeing a fairly consistent response. We look at recoverable sucrose in pounds per ton, a lot of clustering in this data. And this is one of the things you have to look for with tissue concentration data. If you're just taking random samples, you don't always see, because we see essentially that differences in how some of these varieties are interacting with their site. that if you're looking at just a singular sufficiency range, it may not be that there's one, there may be one relative to a genotype by variety interaction. And that's where things, you get into the weeds of some of this tissue analysis, things become extremely complicated. So clustering of points are highly influential. You know, here, if you take these points out, there'd be relatively no relationship between blade total N. It just likely we had one site that may have been a little bit lower that was giving us this relationship. And that's really what was occurring here as well. So that's, you know, kind of the problem when moving forward with some of this stuff. It's getting where we can get into these, looking at a predictive model with tissue concentration. So some main considerations with this: correlation doesn't prove causation. So just because we can correlate something to yield doesn't mean that one's driving the other. It might just be that they're mutually affected by some other factor. And genetics being one of them, environment is the other one. So predicting yield with random tissue samples becomes difficult unless you have a good comparison of a with and without. So you look at a lot of my data where we have with and without a nutrient, I can make a good conclusion based on that data. If I'm just looking at random samples within fields and correlating them, there's really nothing that says that one is causing the other. Again, it could just be that they're both mutually affected by some other factors. And then that book values, they provide a general guideline, but they're not 100% accurate. And that's one of the things that I don't even know where some of the source of some of this data is coming from. So if there is a significant impact of environment on some of these values, you know, the question then is whether or not there's any enough consistency of the data that, you know, we, again, can prove causation. So if your value is this, means that that value, based on what value you have, whether or not you're going to see a reduction in yield or recoverable sucrose. This is the other interesting thing we saw, and this is looking at time 1, time 2, times 3. So looking at 45, 60, and roughly 85 days after planting, seeing this is just looking at total nitrogen concentration. This is a trend we saw in a number of our nutrients where we saw these concentrations decreasing over time. And this isn't uncommon for, it's very common for most plants, where we'll see as a plant ages, it starts to cannibalize itself and starts to shunt some of the nutrients to the reproductive structures. So we tend to see this with some of these elements, that we see that the concentrations decrease over time. And if this is the case, then if you look at just within this 30-day window, we're seeing a fairly substantial reduction in terms of the concentration, which would really indicate that we need a different sufficiency range for these different sampling periods. So it kind of calls to me some doubt of having that wide of a recommendation for a sampling range for a crop like sugar beet, if we're seeing this kind of reduction or change in concentration with the recommended tissue, if it is a plant part from the top of the plant or the newly developed tissue. If it's changing this much, I mean, really, I wouldn't suggest going beyond probably time 2. And I think that's probably the more optimal time for this. But you need to essentially identify sufficiency ranges specific to that time frame moving forward, because I think it's, you know, looking at this change, it concerns me moving forward. And then copper, you see that increase, but this is all from the foliar fungicide applications. So we had some residual left in the leaves from that over time. That one's seeing a slight increase just because of that. And that's the other thing. If you're looking at applications of micros, is there may be some residual impact where it's picking them up. It isn't that the plant is responding to them. It's just that they're showing up just from some of the applications that are on the leaves themselves. But that was the only one that actually increased over time. And that was mainly from the fungicide application. So the numbers here really aren't going to be overly valid for copper, just because we had some contamination from those needed applications of fungicides. So it's one of the things with that. It's the only one that had actually increased. The rest of them decreased or didn't change over time. So an analysis of sampling time, the 40 to 50 days, I think is probably more optimal. And that's what we've been targeting. So around early July, it's kind of what I've been targeting for some of our data collection, because we've got a larger canopy, which is easier to sample, and it's not too late in the growing season where we're sampling more mature plants. So it seems to be kind of, to me, where I would suggest going. I think the 50 to 80 days after planting is too large. These are just some numbers we calculated just based on confidence intervals. It's kind of the average values across some of our given data sets. And I color coded these for ones that are different. I think the ones that are in red are lower than what the anticipated values would be based on the book values. Gray, I think, are consistent, and these might actually be somewhat higher. I can't remember from this, but I know I was looking at seeing how consistent these numbers were to the book values, and I know there's a fair amount of difference in some of this data. So again, you're going to have to be calibrating some of these things really with response trials to get a better idea of what those sufficient ranges are. But interesting data. I mean, just seeing the same thing we're seeing with other crops, both petiole and blade concentrations decreasing as these plants age, which is kind of what I expected, but we didn't have the data really to show that based on the recommended values. So what are things we're looking at? We're just looking at some factors that affected tissue variation. We looked at 22 different environmental or soil factors. We looked at long-term climate factors. 3 out of 22 times these were highly correlated. Soil chemical properties, the soil test values, or some other things like CEC. We saw that in 5 out of 22. You look at some unknown at 3 out of 292. I mean, really, the best we could represent about 34 to 83% of the variation in yield or recoverable sucrose based on some of these tissue concentrations. So it was a wide range in the predictableness. And again, the most predictable seemed to be nitrogen, which I kind of expected because I have a feeling that would be more influential on growth. So that's kind of the issue with it. It's the numbers are interesting and with tissue concentrations, but it isn't the be all end all in terms of predicting yields. So that's been kind of the thing that I've been trying to address with a lot of growers. It's interesting. What I'd really suggest if you're taking concentrations, make sure you have comparable samples within your field, that you have differences in growth, because it's really going to give you the best information than just a random single sample out of a field, because the variability out there is going to be substantial. And if you take a sample in early morning versus late afternoon, you can also see differences. So it's a lot of what we see really with these tissue concentrations are really how the plant's responding to the particular environment it's in, interacting somewhat with some of these other things that you can control, like fertilizer or nutrient availability through fertilizer applications. So they're not consistent over time. I mean, again, I wouldn't suggest sampling much beyond early July if you're going to do it. I mean, the later ones are interesting if you're looking at diagnosing an issue, but again, take comparative samples in your field. And the leaf blade, I think, should be enough for that. You don't need the petiole for that, but that's really what I would suggest, is just trying to take diagnostic comparisons. And then again, just factor in that climatic conditions can be an issue. So if you are sampling a large number of fields, you want comparative data, I'd try to sample the same time, consecutive days at the same time of the day. Don't sample in the morning, then sample a bunch of fields in the afternoon, and then some in the evening, because you may see some differences. Or if you do that, just try not to compare too much between your fields, because you might see some differences. And in particular, if you have different varieties out there, you can see some issues. So it's, kind of one of the things that we're at with this tissue concentration. We can develop these databases, but there's just some clear questions of how useful they are. And I just don't try to read too much in this data unless I know there's a specific problem I'm trying to look at where I want to take diagnostic samples. And that seems to be what this is best in place to handle if you want to take comparative samples within fields.